Good evening, my dear students. Welcome to HashLearn Studios. My name is Dheeraj and I'm your chemistry teacher for the day. And the topic under discussion is extraction of iron and aluminium. So we are looking at the extraction and the metallurgical aspect of iron and aluminium. So like we did yesterday, guys, we're going to recap the previous classes concepts. So we looked at the thermodynamical and electrochemical principles of metallurgy, and I gave you an overview as to how Ellingham diagram needs to be looked at and what really is the basis of Ellingham diagram and what are its applications. So we looked at that aspect, and we solved, before looking at that aspect, we solved some numerical problems as well. In today's class also we'll be solving around 8 to 9 problems, and after that I'll be giving you a brief idea about the metallurgical aspect of iron and aluminium. So moving ahead, this is the CPP question picked up from the given questions from the last class. So we're asking you, in the Ellingham's plot of Gibbs free energy for formation versus temperature, which will slope downwards? So it's pretty simple. Which will slope downwards? If you look at, there's magnesium and there is magnesium oxide. So there is silver oxide, then there's carbon oxide, and carbon monoxide, and carbon dioxide. So if it slopes upwards, it means entropy is increasing. If it slopes downwards, it means entropy is decreasing. If entropy is decreasing, it basically means that the liquid has been converted into a solid, or a gas has been converted into a solid. So if you look at the first one, solid to gas, obviously entropy will be increasing. Second one is silver to silver oxide, again the entropy will be increasing. Third case is carbon, that is usually solid, it is getting converted into a gas, therefore there is the slope will form downwards due to decrease in entropy. So last one is carbon to carbon dioxide, again there is increase in entropy, therefore it has to slope upwards. So decrease in slope, yesterday I told you that for a transition the slopes cannot be straight, it will have cuts in between, and all that points or excerpts from the Ellingham's diagram were looked at, guys. So it's basically to tell you that there is a decrease in the slope, or the slope refers to entropy, there is a decrease in entropy. Moving ahead, the goals for today's class, like I told to you guys, is to discuss some of the important questions pertaining to concepts that we have already looked at, because metallurgy especially will have a lot of factual questions, so you need to remember quite a few things. So we will look at them, and then we will proceed to look at the exhaustive metallurgical aspect of iron and aluminium. So let's move ahead. The next thing that you'll be seeing is a question, guys. So there's 45 seconds time, like you know. So we will go ahead and try to answer this question quickly. Hydrometallurgical process of extraction of metals is based on. So we are giving you a hydrometallurgical process, and we are asking you, the hydrometallurgical aspect depends on what of the following features. So if hydrometallurgy has to work, what of these have to be considered is the question, guys. So you can have a look at it. First one is complex formation, then you have hydrolysis, there is dehydration, and then there is dehydrogenation. So which of it is actually right is the question. Complex formation, dehydration, hydrolysis, and dehydrogenation. So which of it is going to be right? So the clock master says time's up. Think hydrometallurgy, something to do with water. So what happens is the most important case. I'll give you an idea, guys. I'll give you an idea. If you take silver glance, silver glance is nothing but silver sulfide. So if you take this is made to react with sodium hydroxide or sodium cyanide, and you get a complex like this. So when this is made to react with zinc, silver gets thrown out. So silver, which is in the form of silver sulfide, is dissolving. How is it dissolving? By forming a coordination complex, and when I add a more reactive agent compared to silver, that metal of our interest, that is the silver, gets thrown out. Therefore this is how it happens. So we have Sakshi joining us as well as Samruddhi. Welcome to the webinar, guys. You have joined us at the right time, and Samruddhi is right. Complex formation. Hydrolysis, yes, it might look like hydrolysis, but you need to know that hydrolysis will break down the molecule. Hydrolysis basically represents the breaking of or the rupture of bonds using water. But here we are not just rupturing the bonds that is present, we are also trying to convert it into one form which will dissolve in water. Therefore, it is complex formation, and this is just an example that I gave you for it. So let's move ahead, guys. In electrolytic refining, the impure metal is used to make. So it's a pretty straightforward question. If you look at electrolytic refining of copper also, we take pure copper and we take impure copper. So impure copper is taken as what and pure copper is taken as what? If you can recall this, we have the answer. So go ahead, think. A cathode, B anode, C electrolytic bath, and D none of these. Which one is it going to be? Which one is it going to be? 8 seconds left, guys. Cathode, anode, electrolytic bath, and none of these. So the impure metal should always be the anode. It should always be the anode. I'll tell you why it should be the anode. Because anode will undergo oxidation. If anode undergoes oxidation, if I take copper for an example, so the impure copper will become ions, and these ions can then go and settle down at the cathode by undergoing reduction. So it is the anode which is the impure material, and the cathode is the pure material, wherein the pure substances, the ions from the solution will go and get deposited as pure substances. So it's the anode, guys. Pretty simple, straightforward. So remember this. Moving ahead, we have electric refining. Electric refining is again electrolytic refining method only. So electrolytic refining method is used for refining of what? So we are not worried about the reduction part where we look at pyrometallurgy, electrolytic reduction, hydrometallurgy, auto reduction. No, we are not talking about those things. Those things come under the purview of reduction of metal oxides. We are just talking about the last step, which is electrolytic or electric refining. Which of the element will undergo electric refining? These are all factual, guys. You have to know these things. So yes, Samruddhi and Sakshi. Which of these can be used for electric refining, or which of it will undergo electric refining, to be more precise? So lead, copper, iron, sodium. No, sodium is one of the most reactive, and yesterday's class had given you the entire series and what kind of reduction processes it will go. Sodium, one of the most reactive. Copper comes under the third section. Copper comes under the third section along with mercury, silver and iron. So this is one of the least reactive, therefore it is copper. So electric refining is needed for those materials which otherwise will not normally undergo reaction. So copper, mercury, silver and gold, all of these will come under electric refining aspect. So yes, Sakshi corrected her answer, good. So it is copper the answer. Sodium, iron also comes, iron is a little more reactive than copper. Lead and iron's reactivity is almost similar. So lead might be a little more reactive, or I mean a little less reactive than iron, but the copper is the answer, guys. Just look at the previous class of mine, you will get an idea of the reactivity order and which one falls under which purview. Moving ahead, zone refining is used for purification of. Quite a few times in the normal examinations they have asked about zone refining. So zone refining is specifically used for one class of elements. If you know what, you can pretty much answer most questions. So zone refining, is it for copper, gold, germanium, silver? So if you look at the previous order that I gave you, all 3 of the 4 elements will fall under one order and one will not belong to that order. If you can identify that, the answer is yours. So which one is it going to be? Yes, guys, Sakshi, Samruddhi and people who are watching us through YouTube as well, please log into HashLearn app you're looking at it, we are interacting with students, we'll be able to take your questions and interact better, guys. So join us through HashLearn app. Yes, guys, what is it going to be? Keep it in mind that metalloids will always be refined using zone refining. Good. Samriddhi gives us the answer. Germanium, silicon, boron, most of these will undergo refining using zone refining, for a very simple reason that zone refining is based on a principle that impurities are more soluble in the molten state than in the solid state, and specifically it has been observed that the metalloids that are present will have impurities whose melting points are little lower than that of these metalloids. Therefore, they prefer to be in the molten form than in the solid form. Therefore, zone refining uses this principle and hence purification happens. So, metalloid, you can remember, germanium, silicon, boron, all of these will undergo refining using zone refining. So, should not be a big problem for you. Good. Let's proceed. Yes. So, now's the time to tell you that this was a question asked in the previous class. This was a previous class contest question. We had asked you, extraction of zinc from zinc blende is achieved by electrolytic reduction, roasting followed by reduction with carbon, roasting followed by reduction with another metal, roasting followed by self reduction. You need to know that zinc falls under that category of metals which are moderately reactive. So if it is moderately reactive, it cannot fall under self reduction aspect. If it is moderately reactive, it cannot fall under electrolytic reduction. Electrolytic reduction is for most active ones and self reduction is for intermediate to low reactive ones like copper, and since zinc falls in between, it has to be roasting followed by reduction with carbon or roasting followed by reduction with another metal. So the answer is roasting followed by reduction with carbon, because carbon is pretty inexpensive. So if you look at the commercial purpose of mining and metallurgy, it is to extract maximum I would say feasibility of a particular reaction. So the feasibility can be finance related also. Hence we use carbon instead of another metal, because carbon is less expensive and it is even more efficient when it comes to reducing. So hence the answer is this. We have Puspal who gave us the right answer. So unfortunately Puspal is not joining us today, but Puspal gave us the right answer. Congratulations Puspal, you have won yourself one atom session wherein you can get a concept or a question solved by the experts of HashLearn. So let's move ahead. You have the current classes contest question, guys. You'll have 60 seconds time. Go ahead, and the fastest one with the right answer is going to be the winner for this episode, which will be declared in the next class of mine. So the next slide is a question. Here we go. So we are asking you, gold is extracted by hydrometallurgical process based on what? So gold is extracted by hydrometallurgical process based on what? So of being electropositive or being less reactive to form complexes which are soluble, and the last one is to form salts which are water soluble. So what is it going to be? So 27 seconds left, guys. 27 seconds left. So what is it going to be? Time's up. Time's up, guys. So we have Peru joining us. Peru says it is X. Samruddhi says it is W. Then Samruddhi changed it to Y. Okay, Peru also says it's Y. Fine. Let's give a couple of seconds to Sakshi. So let's wait for Sakshi's answer, and then maybe we can take it ahead. So it is simple. Hydrometallurgical process. I think I have already given you the idea, so it should not become a big deal. So let's move ahead. So the fifth problem is, in order to refine blister copper, it is melted in a furnace and it is stirred with green logs of wood. The purpose is, okay, Sakshi has also given us the answer. Good. We will tell you the winner in the next class, guys. So try to answer this question, fifth question, quickly for me. In order to refine blister copper, it is melted in a furnace and it is stirred with green logs of wood. The purpose of stirring the molten copper with green, or the molten ore with green logs of wood, is to do what? To expel the dissolved gases in blister copper, to bring the impurities to surface and oxidize them, to increase the carbon content of copper, to reduce the metallic oxide impurities with hydrocarbons liberated from the wood. So what is it going to be? This process is, if you want the name of this process, the process is called polling, P-O-L-I-N-G, polling. So that word polling should strike a chord in the mind. In order to refine blister copper. What is blister copper, guys? Blister copper is, you take maybe copper pyrites. Copper pyrites is CuFs2. When you take these and when you heat them, especially heating them in Bessemer furnace, that's called as Bessemerization. So when hot air is blown through this ore material, the ore contains copper, iron, and there is sulfur also. So there is copper sulfides formed, there's iron sulfides formed. Along with that, the sulfur also tends to escape as sulfur dioxide due to heavy oxidation that happens due to blowing of hot air. While that is happening, the gas, the sulfur dioxide gas from within the ore material, the molten ore material, escapes, and there are craters or small marks left on the surface, which is called as blisters. So that is blister copper for you. Now from there, he's taking it ahead and telling blister copper is melted and then it is stirred with green logs of wood. The purpose is very simple. So if I take green logs of wood and when I put them into molten metal, which is at very high temperatures, there is decomposition of the hydrocarbons that will take place in the wood. So that hydrocarbons breaks down or decomposes, releasing hydrocarbon gases, which are very good reducing agents. So these reducing agents helps us in converting some of the impurities present into the oxide form. I'm sorry, into the reduced form. That way, metal also gets reduced, the impurity also gets reduced based on their solubility, based on their evaporation capacity, vaporization capacity. They can be separated. So the answer is, it is due to the reduction property of hydrocarbons which are liberated from the green log or the green wood. So both Sakshi and Peru gives us the right answer. Moving ahead, guys, moving ahead. Method used for obtaining highly pure silicon, which is used as a semiconductor material, is. So I already gave you an idea about semiconductors. I've told you which method will be used for semiconductors. Metalloid refining process. So which is it going to be? Oxidation, electrochemical, crystallization, zone refining. Which one is it going to be? Quickly. Should not take us too much time. All metalloids will obviously undergo what refining? All metalloids will undergo zone refining. I've told you that. I gave you an example of silicon, boron and germanium, which you guys answered. So it is zone refining. And to tell you why exactly zone refining is chosen for semiconductors, because the melting point of metalloids will not be as high as that of a metal, or not as low as that of a non-metal. So it will be in between. If it is low, if it is low metals which have low boiling point or low melting point, we can have liquefaction done on them. Or if it is intermediate, we can have zone refining done. If it is too high, we can have other methods also. There's electrolytic refining done or electric refining done. So all of these are based on the inherent property of the material that we are trying to mine out. So it depends on the material. So it is not something that we predict and do. It is based on trial and error basis, wherein we have developed these metallurgical techniques over hundreds of years, wherein they started metallurgy by forging a wheel, and now we have reached a condition wherein we pretty much can extract most elements that is present to us in a most economical way. It has come to us, all of this vast knowledge has come to us as trial and error practices, guys. So it is zone refining. Moving ahead, this should also be easy. Zone refining is based on the principle. I've told you that zone refining is based on one principle. What is it? Impurities of. So Sakshi was the person to give us the right answer in the previous question. Go ahead. Impurities of low boiling metals can be separated by distillation. Impurities are more soluble in molten metal than in solid metal. Different components of a mixture are differently adsorbed on an adsorbent. Vapors of volatile compounds can be decomposed in pure metal. Which one is it going to be? I've given you the theory already. Zone refining, something converts itself into a molten state, something stays as a solid, and then the molten state keeps traveling. So that's exactly what I told you. The time's up. What is it, guys? So Sakshi says 7A. Impurities of low boiling metals can be separated by distillation. If impurities of low boiling metal can be separated at distillation, you need to know, Sakshi, that distillation means where a liquid remains as a liquid and the other liquid escapes as vapors. So usually it is quite difficult to convert a pure metal or a metal with impurities into vapor form, because that would need excessive energy. So therefore, I can give you a reference in Van Arkel method and in Mond's process. We combine the respective metal and its impurity with a respective compound, and the compound's melting point will be way less than that of a pure metal. Therefore, that's how we create a energy efficient technique to convert the metal and its compound into its vapor form. But here, impurity based on low boiling point, I cannot take this as an answer, because these, first of all, you would need too much energy, way too much heat and energy to convert a metal into a liquid in the first place. Then to convert a liquid into vapor is another very tedious task. So distillation is not the right option. If you look at the second option, it says impurities are more soluble in the molten metal than in the solid metal. Yes, what it means is the melting point of the impurities will be a little lower than that of the, a little lower as in I'm talking about 30-40 degrees Celsius, lower than that of the pure metal. So let's say you have a metal M whose melting point is around 600 degrees Celsius. Therefore, by the time you are reaching 600, the impurities would have reached its melting point and it has started melting. So what happens is you have now a melt or a molten condition of both impurity and the metal. Now what happens is metals will crystallize back pretty quickly. So metals will crystallize back and it will form the pure metal, whereas the impurity will remain in the molten form only. And hence in the zone, I have explained it previously, in the zone refining technique, what I do is, if I have a metal and its impurity, I will have a circular furnace. The furnace goes on heating section by section of the metal. Now what happens is, one portion has been converted, the impurity has been converted into its molten form along with the metal. The metal crystallizes back, whereas as I move the furnace slowly, the molten impurity tries to move with the furnace, because it prefers to stay in the molten state than to crystallize back, because all these impurities are found in the lattice structures of the metals. So the metals will crystallize back, whereas these impurities, they find it very difficult to go back and occupy these lattice positions. Therefore they try and prefer to be in the molten form only. Hence, as the circular furnace moves around, or along would be the right word, along the metal, the impurity also gets carried. So the option is 7B. Impurities are more soluble, that is, it prefers to be in the molten metal than in the solid metal. So molten metal, you will have some amount of molten metal traveling along with the furnace, remaining crystallizes out, so the impurity stays with that negligible amount of molten metal and travels throughout, whereas the pure metal goes on crystallizing back. So that is zone refining for use. Let me know if you have any concerns, guys. Now this is the last question for the day. So after this we shall discuss about the metallurgical aspects. So quickly look into it. In the extraction of chlorine by electrolysis of brine, so brine is concentrated NaCl. So in the extraction of chlorine by electrolysis of brine, what happens? Oxidation of chloride ion to chlorine gas occurs, reduction of chloride ion to chlorine gas occurs. For overall reaction, the standard Gibbs free energy change has negative value, a displacement reaction occurs. Which according to you is the right option, guys? Again, this is pretty straightforward. You have brine, so it is not molten. In yesterday's class we looked at the electrolysis of molten sodium chloride or fused sodium chloride. Here we are asking about sodium chloride solution or aqueous sodium chloride. So what is it? Oxidation of Cl minus ions to chlorine gas, reduction of Cl minus ions to chlorine gas. overall reaction delta G naught has negative value, a displacement reaction takes place. So we will start eliminating the wrong answers, guys. By then you will tell us the right answer. A displacement reaction, no, it is not a simple displacement reaction. Oxidation of Cl minus ions, you need to know that the anions move to the anode to get oxidized, and the cations move to the cathode to get reduced. So this chloride ion moves to the cathode. So the overall reaction, I can give it to you. 2H2O plus 2Cl minus will give you H2 plus Cl2 plus 2OH minus. So it's always simple. The anode attracts, or the anions moves towards the anode to get oxidized, and the cations moves towards the cathode to get reduced. So the anions moves to the anode and chlorine gas is liberated. So oxidation of Cl minus ions to chlorine gas. Then straight away I can say reduction of Cl minus ion to chlorine gas is not possible. So since Sakshi told C can be the answer, I'll give you a little logic behind it, Sakshi. If you look at the experimental value as to what would be the delta G naught value of brine's electrolysis, we will tell you that delta G naught for this brine's electrolysis is around plus 422 kilojoules. So outrightly I can tell that delta G naught does not have a negative value, delta G naught has a positive value. Then if it has a positive value, what does it mean? It means it is non-spontaneous. If it is non-spontaneous, how is it that I'm making the reaction happen? That is exactly why I'm doing electrolysis, wherein electricity from outside is forced into the electrolytic cell and the reaction is made. Correct? So the reaction has to be positive here. It is positive, hence non-spontaneous. I'll tell you how it happens. So if you know the formula, delta G naught is equal to minus NF E naught. Therefore, E naught is equal to minus delta G naught divided by NF. So delta G naught value I've given, which is around 422 to 424 kilojoules, and N and F I know how many electrons are being exchanged, and F stands for Faraday. So once all of these data is input, this answer comes up to around 2.2 to 2.3 volts. So you have to apply greater than 2.2 to 2.3 volts in order for this reaction to happen. If it would have been spontaneous, we wouldn't have looked at the electrolysis as in an electrolytic cell. It would have been spontaneous electrolysis otherwise. Are you with me? So the moment I take NaCl and concentrate, there should be evaporation of that is liberation of chlorine gas, which doesn't occur, which occurs only when I apply electricity. That is because the delta G naught is positive, making it non-spontaneous. This reaction will not be feasible. Yes, Sakshi, that's exactly right. It won't be feasible, and hence this is a reason as to why it won't be feasible. So hope you have got a clearer picture now. Yes. So moving ahead, like I said, we have completed the 8 questions that we had allotted for today's class. So we will move ahead. I'll give you a glimpse of how the aluminium and iron metallurgy happens. So we will begin with aluminium's metallurgy. So to talk about aluminium's metallurgy, it starts with a couple of ores. I can have bauxite, or I can have kaolin, or cryolite, feldspar. I'm not going to give you the chemical composition of all of these, because the chemical composition of all of these is looked at, guys. So we're not going to need all of that. There can be corundum, or there can be orthoclase. So these are some of the common ores of aluminium that I have. So how is the purification done? The purification is done using a method called as Bayes process. So what is this Bayes process? Bayes process is I take alumina and I dissolve it in NaOH, and I get solubilization of aluminium taking place. I have solubilization of aluminium taking place. So Sakshi is asking, so won't both option A and C are correct for the 8th question? So let us try to answer that question. I'll quickly go back. So Sakshi says for overall reaction delta G naught has negative value. Delta G naught does not have negative value for both, Sakshi. If you look at this, if it would have had a negative value, the reaction should have been spontaneous. So you yourself said that the reaction will not be feasible. Yes, the reaction is not feasible, therefore then delta G naught value has to be positive. If the reaction would have been feasible, I don't have to supply this 2.2 to 2.3 volts of current. The electrolysis process would have happened just like that, wherein the chlorine gas should have liberated from the anode and it is hydrogen which should have liberated from the cathode. So if this has to happen on its own without any of our interference, we would have called the reaction to have delta G naught a negative value, spontaneous. But delta G naught does not have a negative value, hence we have to supply electricity from outside and make this reaction happen. Let me know if you have any questions in specific. Yeah, moving ahead. This reaction happens, Bayes process, where alumina or one of its ore form is solubilized to give you this form. This is the soluble form. What is the advantages? The advantages is insoluble impurities are removed. Insoluble impurities are removed because the only ones which are soluble will move in. The soluble one is the actual ore. The rest of the impurities will be removed. Next, in the second case, this is step 1. This is Bayes process step 1. In the second case, this is acidified, and once, this is acidified, and once this is acidified, I will have aluminium hydroxide precipitating along with formation of water. Now you need to understand that aluminium precipitate has very low solubility product. You would see it in equilibrium. Since its solubility product is very low, once a precipitate is formed, it will not become a solution back. So I have solid aluminium hydroxide precipitate. This aluminium hydroxide precipitate can be heated to have aluminium oxide, and the aluminium oxide so formed will be in the pure form. So that way I've removed the insoluble impurities by dissolving the ore material in a solvent which will make alumina soluble. Okay, now moving ahead. So Sakshi, yes, I'm glad that Sakshi has got it. Good. Now moving ahead, guys, the complex is decomposed. Next, what happens is you have alumina. We have finished the first set of exercise, that is, I've separated the impurity from the ore material. Now I have the pure ore material. Now what shall we do? One half of the work is done. Moving ahead, the second aspect of metallurgy is electrolysis of Al2O3, which is called as Hall-Heroldt's process. Again, this is a very important theory exam for your boards, 12th boards also. So Hall-Heroldt's process. What happens in Hall-Heroldt's process? Let us not get into the details of it, but I'll tell it to you in the form of a reaction. So you have carbon undergoing reduction at cathode, oxidation at cathode, I'm sorry, to form carbon dioxide plus 4 electrons. This is at anode, oxidation at anode, and at cathode you have reduction. So aluminium 3 plus is undergoing reduction to form Al. So you can balance the reaction, multiply this 3 times and multiply this 4 times. Therefore the overall reaction will be 3C plus 4Al 3 plus, giving okay. Give us a moment here, guys. Give us a moment here. Yes, sorry about that technical glitch, guys. So let's move ahead to what we were talking about. So yes, okay, so we have the slides misplaced a little, no problem. We will go ahead. Now I was talking to you about the different ores, and I spoke to you about Hall-Herold's process. I'll rewrite the Hall-Herold's process reaction. You can look at this here, Hall-Herold's process. Yes, we are back. Hall-Herold's process. You will have at anode, you will have oxidation happening. So carbon is oxidized to carbon dioxide. Carbon dioxide along with liberation of 4 electrons. At cathode, you will have Al3 plus undergoing reduction to form Al. I can balance the reaction. I did that in the previous slide by multiplying by 4 and 3 by the respective number of electrons, and the overall reaction goes up to 3C plus 4 Al plus 3 plus 6 O2 minus, giving us 4 Al plus 3 moles of carbon dioxide. This is Hall-Herold's process, guys. Pretty straightforward. What should I be concentrating when it comes to metallurgy of aluminium or metallurgy of iron for that matter? You should be concentrating on what are the ores that I would be taking, the probable ores, because there are quite a few. You don't have to remember all of them. What are the probable ores? How is the ore purified? Which method is used in concentrating the ore? Is it leaching? Is it Froth flotation? Is it the other technique, the water-based methods? How is it being used? How is it being concentrated? Point number one. With respect to that, we saw that it is the Bayer's method, wherein alumina is, that is aluminium oxide, which is also called as alumina, is dissolved in NaOH, and that way it gets purified. From there, we take it ahead and we try to extract it using Hall-Herold's process, where I get aluminium. So this is how it happens. Now if you want, I can give you the entire reaction, guys. The entire reaction is going to happen this way. So you will have this, I think this would be more ideal. So I can say this would be more ideal. So you can start with bauxite, the ore. So once you start with the bauxite, you will use NaOH. You can remember this better. You will use NaOH, and both of them is ingested into a digester. A digester is a processing unit wherein the bauxite dissolves, that is the ore dissolves in NaOH. Now whatever comes out from here is allowed to settle. So this tank will allow the settling of sediments. So the undissolved impurities will settle at the bottom, whereas the actual bauxite ore has dissolved in the solution. Now the next thing that I do is I let them precipitate. So I let the iron oxide, aluminum oxide material precipitate. So once I precipitate, the entire container is now filled with solids of aluminium hydroxide. The solids of aluminium hydroxide is put into a furnace or a kiln. Wherein heating happens and the moisture is removed, and now I have Al2O3 left. And this Al2O3, this was your overall first process, Bayer's reaction. Now the Al2O3 is fed into an electrolytic cell. It is fed into an electrolytic cell, which converts the aluminium oxide into aluminium. Therefore, this aspect here is the last part that we discussed, Hall-Herold's process, and this entire thing comes under Bayer's process. You just have to remember the overall flow, and you have to know the reactions involved. So I've given you the reactions for both. That way it should suffice, guys. So this is about extraction of aluminium. Now we shall look at the extraction of iron, zinc and magnesium in the upcoming classes. That's in the next class of mine, which is on Tuesday. So we have looked at the metallurgical aspect of aluminium in this case. So we have iron to go, very important. So I'll let you know what are the crucial aspects into which you will have to dwell a little deeper, because there's smelting processes, there's blast furnace, there's quite a few other things that you have to look at. And zinc is another very important commercial metal. So zinc along with magnesium and iron shall be looked at in the next class. So moving ahead. To quickly summarize today's class, we were supposed to look at extraction of iron and aluminium, which we will look at aluminium in the next class, because we have pretty much a lot of stuffs to be included. So time constraint is one thing, and apart from that, we looked at a good number of questions in the beginning, which should act as a concrete block in making your understanding of the previous concepts even more rock solid. So I hope today's class was evoking and enthusiastic. So if you have liked the class, go ahead and share this among your friends and help them as well, guys. And CPP is it's CPP type, so passport subscribers, please go ahead and solve the questions that I've picked up for you, some of the important questions. And for non-passport subscribers, CPP is locked. All that you have to do is to subscribe to passport, which is just a click away, and it gives you not just access to the questions that we experts pick for you, but also it gives you 24/7 access to one-on-one doubt solving sessions. So at any point of time you have a doubt, you post a question and it gets answered within no time. So that becomes very crucial in building your fundamentals, and also to answer a question which is posing as a hindrance to move in further studies. So apart from that, it gives you access to practice questions, tests from some of the best-selling books, and also all the video classes covering the toughest concepts and problems. So even though we are giving you the theory while we are covering the questions, the in-depth theory and the in-depth points needed will be covered in the, or has been already covered in the video classes, so you can go and have a look. That is definitely going to be a bonus for you guys. So it'll be Dheeraj signing off for now. The next class of mine is on Tuesday, so waiting for your active participation on Tuesday's class of mine. See you. Good night.